let's look at an important topic that we'll have to use to solve the questions with this topic, which is shell mass balance. The diffusion problems in this chapter are solved by making mass balances for one or more chemical species over a thin shell of solid or fluid. Having selected an appropriate system, the law of conservation of mass of species A in binary system is written over volume of shell in the given form. Rate of mass of A in minus rate of mass of A out plus rate of production of mass of A by homogeneous reaction is equivalent to 0. The conservation statement may of course be expressed in terms of mole instead of mass. The chemical species A may enter or leave the system by diffusion, that is, by molecular motion, and also by virtue of overall motion of fluid, that is, by convection. Both of these being included in Na. In addition, the species A may be produced or consumed by homogeneous chemical reactions. After a balance is made on a shell of finite thickness by means of the above equation, we then let the thickness become infinitely small. As a result of this process, a differential equation for mass or molar flux is generated. If into this equation we substitute the expression for mass or molar flux in terms of concentration gradient, we get differential equation for concentration. Now, since this is a differential equation, we'll have to integrate it and then we'll get one or more than one constants. To remove those constants, we'll be using boundary conditions. When this differential equation has been integrated, constants of integration appear and these have to be determined by the use of boundary condition. The boundary conditions are very similar to those used in heat conduction. The concentration at a surface can be specified. For example, XA is equal to XA0. The mass flux at a surface can be specified. For example, NAZ is equal to NA0. If the ratio is known, this is equivalent to giving the concentration gradient. If the diffusion is occurring in a solid, it may happen that at the solid surface, substance A is lost to a surrounding stream according to the relation, which is Na0 is equal to Kc into Ca0 minus Cab, in which Na0 is molar flux at the surface, Ca0 is the surface concentration, Cab is the concentration in the bulk fluid stream, and the proportionality constant Kc. And the final boundary condition will be the rate of chemical reaction at the surface can be specified. For example, if substance A disappears at a surface by first order chemical reaction, then Na0 is equal to K1 double prime into Ca0. That is, rate of disappearance at a surface is proportional to the surface concentration. The proportionality constant K1 double prime being a first order chemical rate coefficient. Now let's look at sample shell mass balance in terms of moles as well as in terms of mass. Shell mole balance. We'll be looking at a 1D plug flow which has component A. Where FAZ will represent molar flow rate of A at position Z, and the unit will be mole per second. RAZ will be rate of generation or consumption of A per unit volume, and the unit will be mole per second meter cube. AC will represent the cross sectional area of the tube. Now, applying mole balance on species A. The general equation being input minus output plus generation minus consumption is equal to accumulation. At steady state, which is our assumption for keeping the thing simple, accumulation will be 0. FAZ, which is the input, FAZ plus delta Z, which is the output, plus RAZ into AC into delta Z. This will be our equation. Divide this equation by delta Z. FAZ upon delta Z minus now multiplying this equation by -1. And then rearranging the terms. Now we know that using the definition of differentiation, FA Z plus delta Z minus FAZ divided by Z is equal to dFA upon dZ. RAZ into AC is equal to dFA upon dZ. This will be our final differential equation in terms of moles. Now this equation can also be converted into terms of concentration depending on our problem. So let's look at that as well. CAZ is the concentration of A in mole per meter cube. And FAZ can be substituted as CAZ into U into AC, where U is the linear velocity in meter per second and AC is again cross-sectional area. If we take the assumption of U as constant and again apply the equation of in minus out plus generation minus consumption is equal to accumulation. Now continuing with the calculation, d by dz CA into U into AC is equivalent to RA into AC. Since U is constant and AC is constant, we can take them out of the differential. U into AC d by dz of Ca is equal to Ra into Ac. And the final form of this equation will be something like this, where U into dCA by dz is equal to Ra. According to the question given, we can use either this equation or this equation. The only difference being one is in terms of moles, another is in terms of concentration. Now let's look at it from in terms of mass. Shell mass balance, 1D plug flow again, in which A is a component. We will consider shell as a differential slice of length delta Z in a pipe or reactor. The notation will be as follows, where MAZ will be mass flow rate of component A at position Z, and the unit will be kg per second. RAMZ will be mass rate of generation or consumption of A per unit volume, and the unit will be kg per second meter cube, and AC will be again cross sectional area. Of the tube, and the unit will be meter square. Now applying the general equation, input minus output plus generation minus consumption is equal to accumulation. Since our assumption of steady state still holds true, accumulation will be equal to 0. So the equation becomes MAZ minus MAZ plus delta Z, which is the output, plus generation, which is RMZ AC into delta Z. Now, using similar methods as we used in moles, we'll divide this entire equation by delta Z. Now multiplying this equation by minus 1. Now let's rearrange the terms. We know from the definition of differential equation MAZ plus delta Z minus MAZ divided by delta Z can be written as dMA by dZ. So substituting this into the above equation, so this is the final form of the equation in terms of mass. Use similar to above where we converted moles into concentration, we can similarly convert mass into terms of concentration again. In here it will be in terms of, so this is a final equation in terms of mass. We can convert this equation again into in terms of mass concentration, similar to the above way where we converted moles into concentration gradient. So let's look at that as well. If rho Az is defined as mass concentration of A with unit kg per meter cube, and U is again linear velocity with the unit meter per second. So MA can be written as rho A into U into AC. Substituting this into the above equation, now we know that U and AC are constant, so we can take them out of the differential. AC will get cancelled and the final equation will be very similar as to what we found out in terms of concentration gradient.
Now let us solve a question on diffusion with a heterogeneous chemical reaction. A simple model for a catalytic reactor is given where A reacts to give B is being carried out. We imagine that each catalyst particle is surrounded by a stagnant gas film through which A has to diffuse to reach the catalyst surface as shown in figure. At the catalyst surface, we assume that the reaction 2A gives B occurs instantaneously and that the product B then diffuses back out through the gas film to the main turbulent stream composed of A and B. We want to get an expression for the local rate of conversion from A to B when the effective gas film thickness and the main stream concentrations are XA0 and XB0 are known. We assume that the gas film is isothermal, although in many catalytic reactions the heat generated by the reaction cannot be neglected, but here we will neglect it considering it as an ideal condition. Here A enters into the reactor, spheres with coating of catalyst material is there present, and A reacts with the catalyst to give B. Now here we can see that the length of stagnant gas film is del, and on the surface of catalyst concentration is decreasing. Now we know that from the stoichiometry of the reaction 2A gives B, the molar flow rate of NBZ would be half and opposite to Na at Z. We know that combined flux Na at Z is equals to molecular flux plus convective flux, which is NaZ plus NBZ. This is molecular flux and this one convective flux. Now putting value from equation 1 into equation 2, we get taking this on the right side, taking this on the right side, we get molar flux of A at Z equals to minus of C dAB upon 1 minus half, just a second, here should be XM.